This is the last topic, our very last topic on CP2, and we're gonna now do optics. So optics has two parts. One is geometrical optics, and the second one is physical optics. But we're not gonna do physical optics. We're just gonna do geometrical optics. So physical optics is has a part like interference, diffraction of light, just like you guys did in sound wave interference. But we're just gonna do the geometrical optics. So we're gonna do laws of these are the topic. So first we're gonna consider light as a ray of light, reflection and refraction, total internal reflection, and the thin lens and the image formation by thin lenses. So these are the topics. This is going to be the topic. So first of all, in geometrical optics, we consider light as a ray. It travels in a straight line, and you can just define light as a beam of light ray. By the straight line, just like this. Laser light rays. So here, you point a laser light, it travels in a straight line, so just like that. And if you just see this visual light, even the light travels in a straight line like this. So this is going to be our model. Uh, so, but just to remember that light in depth, actually, light is an electromagnetic wave. It's a wave, and but you can still assume light as travels in a straight line because that's just the path actually, that the wave travels. So these circular waves are spherical. Spherical light travels as a spherical wave, but the direction, perpendicular to this spherical wave front represents the light rays. So light rays is just the direction where these waves travel, and you can just consider light as parallel beam. So next is the very first law. A very simple law is law of reflection. Law of reflection says the angle of incidence and angle of reflection should always be equal. So for example, this is your surface. If the light ray strikes here, right? So this is the incident wave or incident light ray, and uh, it will reflect in such a way that it will make same angle of incident. This is the angle of incidence, this is the angle of reflection, and with but these angles are reference to the normal, this imaginary normal drawn to the surface. And based on the law of reflection, it simply says the angle of incidence and angle of reflection must be equal. So very easy law. And the second part of this law is the incident ray, reflected ray, and normal. All they must lie in the same surface, same plane. See here, this incident ray, normal, and the reflected ray, right? All should remain in the same surface, same plane. This is the plane they must lie, all lie. So that's what it says. And the law of reflection of light is obeyed by both actually a smooth surface like this, or any polished surface, or even even a rough surface must obey law of reflection because so for each incident, right? You draw the normal, imagine a normal. The angle of incident and angle of reflection is still equal, right? So here, when light strikes here, the angle of incidence and angle of reflections are still equal. See, but your normal orientation is different. This is your normal now. So and this kind of reflection is called diffuse reflection. Right? And next is just like reflection, the refraction of light. So what is refraction of light? First of all, refraction is the bending of light when it passes from one medium to other medium. This phenomenon is called refraction of light. And in depth actually is because of the change in speed of light. And why does the light change its speed? It has a big physics behind that. We're not going to talk about that in details, but the bending of light is mainly because of the change in speed of light when it enters from, say, low density material to high density material, something like that. This is the incident where some light will be reflected, some very low percentage of light will be reflected out still. And this is the refracted light, right? This is called refracted light. This is the actual picture done on a glass slab. And this is the emergent ray. This is called refraction of light. Okay. And just like reflection, refraction has some laws. It's called Snell's law. The law of reflection of light is called Snell's law because he invented that. It simply says this. This equation is simply Snell's law of refraction. So it says n1 sine theta 1 is equal to n2 sine theta 2 and so on. So what are n and n2? So n1 and n2 are the index of refraction. It's called depends on the density of the medium. So different media has different index of refraction. So that's what it says. So first draw. This is the incident ray, and this is the normal right drawn to the surface. And the ray will bend and make an angle of refraction. This theta two is the angle of refraction. And what's their relationship? So relationship is this: n1 sin theta 1 is must be equal to n2 sin theta 2. That's how light behave. Light bends when it passes from, say, air to glass or air to water, and the other way around. Okay, so so remember n1 and n2. N is the index of refraction of light, depends on the medium. And these are some, you can clearly see the different index of refraction for different material, right? So the common material is water. Water has 1.33. Glass has about 1.5. If it doesn't say any glass, it's just consider 1.5. But ground glass has 1.52 and flint glass has 1.62. Diamond has got the maximum index of refraction because it's very dense. And this website you can see, actually this applet you can see why does the light bend. You can see in detail this website, but you don't need to know right here. Okay, so some basic rules again, just exploring various possibilities of Snell's law. So first of all, when light going from n1 to n2, right? So when uh, if um, so from Snell's law, right? Snell's law said n1 sine theta 1 is equal to n2 sine theta. So what happens if n1 is equal to n2? Obviously, light will not bend, right? You can clearly see. And I'm going to show you the picture about that consequences. Okay, next. So when light bends from brighter to denser, right? So when light passes from, say, air to glass or air to water, light bends towards the normal. Why? Because from this formula, since n2 is n1 because sine theta 1 is n2 sine theta 2. So since n2 is greater than n1, since they are inversely proportional, right, they go opposite. So theta 2 has to be less than theta 1. So light bends towards the normal. Okay. So light bends towards the normal. Just this is the example actually. Light passes from say air to glass, light bends towards the normal. And opposite will happen when light travels from denser to rarer, right? So say glass, right, to air, light will bend away from the normal, like that, because theta 2 is greater than theta 1 based on the Snell's law. That's how you check, Snell's law in different scenarios. And here's an example. You can also check this video. When light, so when light passes from one medium to other medium with the same index of refraction, light doesn't bend, right, from Snell's law. And here's the interesting consequences. This is a corn oil, okay, Western corn oil, and interestingly, the corn oil has exactly same index of refraction as the glass rod. Okay, this glass rod index of refraction and corn oil index of refraction are exactly same, and that's why you see, actually you can see the glass rod here, right? The glass rod suddenly actually disappears in this corn oil because why? Um, because their index of refraction are equal, and since light doesn't bend, and you don't actually see the glass rod inside the corn oil because the light has to bend somehow in order to see inside the oil. And you can check this video as well. And the other way you can calculate the index of refraction is there's another formula from this is from Huygens principle, actually, wave theory of light. So index of refraction can also be calculated by using this. C is the speed of light in vacuum, which is the maximum speed limit. You can see this very important number, 328 meters per second. That's the speed of light in air or vacuum, which is the maximum. And V is the speed of light in medium. So just by taking this ratio, if you know the speed, you can calculate the speed of light. You can calculate the index of refraction. Okay, the next is real and apparent depth. And you might have seen that actually. If you put a coin in a beaker filled with water, right, or any liquid, and if you view it from different side view, this coin actually appears to lift up, right? It appears from here. And this is called apparent depth. That's why it is called apparent depth. And this is the real depth. And another example is, for example, 10 feet deep pond would only appear to be about 7 feet deep when viewed from above, right? And this is, again, all this happens because of this illusion happens, optical illusion happens because of the refraction of light, because light has to bend, because this is the real position of coin, right? And the light, see, from here will travel here, and at the boundary it has to bend, and we know when light goes from water to air, it has to bend away from normal, right? Away from normal. So that's why. So same thing happened this corner. And for you, for observer looking from outside, this coin actually just appears here. Just trace it backward, right, like this, and this coin appears here. And this is the virtual position of the coin. And you can also find the relationship between real and apparent depth by just taking this ratio. You just play with geometry. And the real depth divided by apparent depth is just happen to be the index of refraction. And same thing happened. So this is the diver, right? And the instructor is seeing from above. So the for instructor, her the diver's apparent position will be somewhere here, right? And the opposite will happen actually if the scuba diver, right? This diver wants to see her instructor, it will appear from here, and this all happens, you know, and these are all examples of bending of light, due to refraction of light. So the pencil in a beaker, glass of water appears broken, right? And it's again because of the bending of light, because what you see inside the water is just the apparent position, not the real position, and it just appears broken. And there are some other examples you can take, right? So here's the question. So figure shows a fish and a fish stalker in water. So the first question is, does the stalker see the fish in general region of A or B? Right? And second question is, does the fish, the other way around, does the fish see the eyes of the stalker in general region of B and C? So if the stalker sees the fish, where is the apparent position of this fish? That's the first question. And to do that, you have to do this. Draw, choose any, pick any point at fish. So I'm just picking eye, right? And draw the ray of light. It will strike at the boundary, and what will happen? Then next, it will bend, right? Because it has to bend away from the normal. And for observer, for fish stalker, it just appears from here. So this fish stalker will see the apparent position, the virtual position of the fish at general region A. Now, does the fish see the eyes of the stalker in the general region of C or D? Now, do the same thing. Pick any point on the stalker. So I'm going to pick this eye, and the light will strike like this, and it has to bend towards the normal, right? Towards the normal because of. But for fish, it will just produce it backward. It's extrapolate light backward. It appears from C. So the next important phenomenon in geometrical optics is something called total internal reflection, or in short TIR. Okay, total internal reflection. It's a very important phenomenon. So this is the thing actually. You will see total internal reflection only if light passes from strikes from higher index of refraction to lower index of refraction, not the other way around. Okay. So here's the thing. So if you have a source of light inside the water like this, and the light right at shallow angle, actually light strikes like that. But what happens if you gradually change the angle of incidence, right? This is the angle of incidence, underwater, what will happen? The angle of refraction will change very rapidly, right? And at some point, it will pass us through the boundary. See this, and this angle is called critical angle, where the angle of refraction is 90 degrees. Okay. And after, even if you increase the angle of incidence slightly less than half a degree, then it will bounce back to the same medium, back to the same denser medium. And this phenomenon is called total internal reflection. 100% of the light will be reflected. Okay, it's a very efficient way of reflecting the light. So 100% of the light, you know, 100% reflection, you can say, total internal reflection. So this phenomenon is called total internal reflection, and you can clearly see right here. So here, no total internal reflection. Most of the light ray will refract, right, to the air, and this is water. So if you keep increasing, this will happen. Some part of the light will be still reflected, but after critical angle, what will happen? So all the 100% of the light will be reflected back to the same medium. Okay, this is called total internal reflection. This is the total internal reflection. And here's the animation I have done to understand this. So this is critical angle, right? By definition, and then after that, it suffers total into 100% reflection after critical angle. So this phenomenon is called total internal reflection. And remember, to see the total internal reflection, the light has to go from higher index of refraction, let's say water, right, to some lower index of refraction. Okay. You won't see this phenomenon when light passes from air to glass. So how do you find the critical angle for given interface? So it's very easy. Just use the Snell's law, right? So then, so critical angle is like this, right? So when light uh, strikes like that, and when the light refracts through the interface, making angle of refraction 90 degree, right? Um, this angle is called, we call critical angle, right? The angle at which the angle of refraction is 90 degrees is called critical angle. Just using this and just Snell's law, n1 sin theta 1 is n2 sin, but yes, sin theta 2 is 90 degree, right? And then sin 90 is, this is 1, and then n2, and then solve for critical angle. So critical angle is then inverse sin n2 over n1, right? So this has to be always denser, remember. So this has to be rarer, right? Otherwise, sin theta will be more than 1, it won't work. Okay, so quick check actually. So when does the light suffers total internal reflection, and when does the light passes from the upper medium? If this is the check, if the angle of incidence in the denser medium is less than critical angle, it will just do regular refraction. It's just regular refraction. It follows Snell's law and just a regular refraction. Okay. So when the angle of incidence is less than critical angle. Okay. But as you see, when the angle of incidence in the denser medium is greater than critical angle, then it suffers total internal reflection. That's how you check. In your calculation, you will see, I will show you in an example calculation. And the total internal reflection has many interesting, applications in real life. Actually, it's the optical fibers, because now because of total internal reflection, right, the light can pass actually through a zigzag path. Light never comes out. Light never has chance to escape out of the fiber optics. Fiber optics is just made from plastic or any other material. And if you shine a light from here, you can clearly see a light suffers total internal reflection internally at each boundary, at each reflection. Here, you can see this is total internal reflection, right? Total internal reflection, right? This is TIR. And then light never get chance to escape from the surface, and it just travels inside the pipe, right? Fiber optics, and then you can send signals, any signals through using optical fiber, and it's very efficient way of sending the signal, actually data transmission, very fast data transmission. And many of the other examples are the high quality binoculars or telescope use the use of total internal reflection. So there is a minimum loss due to reflection of light, refraction of light. So here almost 100% of light will be, you know light will be transmitted from the object. So this is the um, light from distance object, right, passes almost 100% light will be collected because of use of this special prism, glass lens. And here's the other example I can show. So we can easily do it in the lab actually. So you just need a water bottle with a small hole. There's a small hole right here, and you shine a laser light. And because of the total internal reflection, right, the light actually always stays inside this water pipe. You can clearly see light stays inside the water pipe, right? And it's because of this. Because at its bounce, right, it is internally it suffers total internal reflection, right? It never a chance to escape from the surface because of total reflection. Other example is if you are a diver and try to see the outside sky from underwater, you won't see the full vision. And it's again because of total, and this is the real picture actually. So you will see the outside sky through a small hole, depending on how deep you are. So we can calculate this diameter. You will just see the sky, upper sky through a hole having certain diameter depending on the depth. And it's again because of the total internal reflection. Because for a diver, right, this is the field of vision. The field of vision, the diameter of the hole is dictated, right, is controlled by this critical angle. So you just need to calculate this critical angle. This is where you will see the sky actually. Everything else works as a reflecting surface, a mirror surface, reflecting surface. You won't see outside world. Our last topic in optics, geometrical optics, is image, especially image formation by lens, through thin lenses. Okay, and image science, image is a very important application in optics. And you can see there are basically two types of image. Of course, real image and virtual image. Okay, so what are those? So real image is the image formed by actual convergence of light rays, like this, right? It's actually is so the image formed by the convergence of light. Okay, converging beam of light is called the real image, and the best example is the projector light. So or so because projector actually project on the actual screen, and the image is really there actually physically. So the best example is the image formed by the projector, right? The project, because projector has a lens. The virtual image example is virtual image is the image formed by the diverging rays. Okay, uh, so image formed by the diverging rays, just like that, right? Best example is the image formed by the mirror. Okay, image formed by mirror. The plane mirror is an example of it. Because virtual image, because you can see the face right behind the mirror, but your face doesn't really exist, right? Behind the mirror, because it just appears. You just see it just appears to come from here. So that's why it is called virtual image. And here's the image formation mechanism of, so plane mirror forms image because of the reflection of light. So here, in an object, you place an object of any size in front of the mirror, and the object, object sends, many beams of light rays, right, strikes the mirror, and each of these light rays gets reflected like this, right? And then but they are diverging, see, they're all diverging rays. After reflection from the mirror, they diverges, so that's why it is a virtual image. And then to see the virtual image, right, you're seeing from here, you're the observer, you will see it just appears, because you have to now produce them, extrapolate them backward with the dotted line means virtual image. And it just appears here, the image of that object appears here, right? And this is the example image, right? That's the mechanism. And same thing you can put at different locations and different height, and then it's the same thing. So the main idea is the image formation of plane mirror is because of reflection of light. And the common mirage you will see is also actually because of reflection, because during the hot days the road actually just appears reflecting, right, reflecting surface. And because of the same thing actually, because now we already know total interreflection during hot days, the air molecules just above the surface, right, road becomes hot. Hot means less dense. but the layer above that is still cold, right? So any object, right, light rays from object will follow this path actually, because it's now going from higher index to lower index, right? Higher index to lower index, and it slowly at some point it suffers total interreflection, TIR, total interreflection. Then for observer, for you, right, it just appears from here. This is the virtual image, right? This is the apparent image. You say virtual or apparent image, and that's it just appears from here reflecting. So that's the reason actually this road just appears reflecting surface. Uh, and these are the common mirage you will see. This is the common desert mirage you will see, and this hot desert, this all these are looks pond, right? This water looks water, right? Because of the mirage, this optical illusion, because of total interreflection. It's actually not water, it just appears reflecting surface because of the total interreflection I just explained, right? I just explained here. Our last part is of the image formation is the image formation by refraction, or basically even image formation by lens. So lens, your camera or even your eyeball, human eyeball has a little converging lens, and because of that lens, it helps focusing the light on the retina, and then you can see the image. So we're going to talk about that. So here's an example. These are all examples of image formation by refraction, or refraction of bending. So you'll see the color image, the rainbow color. It's also because of the refraction of light, because of the diffraction of light actually. Because light rays has 7 different visible colors. That because they've been because their index of refraction for the given medium is different for different colors. So they bend differently. So that's why you see the color. So our main topic here is the thin lenses, image formation by thin lens. Thin, we call thin because its thickness is really small compared to its diameters. So there are uh, you know lenses actually: converging, also called convex lens, and diverging lens, also called concave lens. You can clearly see this real picture. So this type of lens is called converging lens. Okay, converging lens. Why? Because if you pass a beam of light rays, it will converge. After refraction, on the other side, it will converge. That's why it is called converging rays. Right? You can clearly see converging. Right. On the other hand, look at the shape. This is called diverging lens or concave lens. So because if you pass a light rays, right, it will all the light rays after refraction on the other side will diverge, right, and that's why it is called diverging lens or concave lens. And there are many applications of lenses, so you find lenses in everywhere actually. So your spectacles, your glasses are have lenses. All the high quality microscope, telescopes have lenses. Even your eyeball has lens. And so the first thing we're going to study in lens is the defining the focus or focal point of the lens. So how do you find the focus or focal point of the lens? So it's easy actually. You have to pass a beam of parallel rays. See, parallel rays. And for converging lens, what will happen is after passing a parallel beam of light rays, they will all converge at a single point, and we call this our focus. And the distance from the center of the lens, right here, to the focal point or focus is called focal length. So what's going to happen in diverging lens or concave lens? So you still pass a parallel beam of light rays, and they will diverge instead of converging, right? They will diverge, and then you will have to trace them backward like this. You'll have to extrapolate them backward with dotted lines. And this is where the image here or the focus will be virtual. You will have to say virtual focus for in case of concave lens, diverging lens, right? The image just the focus just appears for uh, it just appears to come from here, right? Because this focus is formed by the diverging lens. So in case of concave lens, that's how you find the focus. And this focal length is, since it is a virtual, this focal length is negative for diverging lens. And here's an example. right? So a lens can form a lens. The given lens can form both an inverted and upright image. And how? What's the physics behind that? What's the science behind that? You know, it all depends. You will see. It all depends on object distance. Okay, where you put an object. And to find this, you know, to find the position of the image formation. So these are some rules you need to follow. Okay, these are some techniques. So you actually need only two rays actually to trace the image diagram to see to find the position of the image formed by the given lens. First, you need a P ray. P means parallel ray, approaches the lens parallel to the axis, right? And the other one is you need actually no, you don't need F rays actually. So, but in cases if you need F ray is drawn towards the concave or the convex focal point, right? And the next one, so you just need this P and M rays actually, okay, to find the position of the image. You will see next point, next page. The midpoint ray is the M ray, goes to the middle of the lens and it doesn't go deflected. It won't deflect if you pass a ray of light to the middle of the ray. So here's the example. Okay. So first I'm gonna show you for a convex lens, for converging lens. In case of you just need a P and M ray, okay. You may not need actually F ray actually necessarily. First, you put an object, right? This is the object, real right object of some height, and say this is the defined because first you need to put the focal point because the given lens has focal point, the focal point, focal length, right? Focus will be given to you. So put it somewhere here, and what you need to do is first draw the P ray. P ray means parallel to the this axis, right? And what we definitely know that any light rays, parallel to the principal axis, will go through the focal point. That's why we choose the P ray. So here's the trick, right? Let me tell you again. So any rays parallel to the axis has to go through the focal point. And the next is the M ray, right? M ray is now choose another ray passing directly through the center of the lens, and it will go undeflected. That's how light rays behave. We definitely know that this ray will not bend. This will just go, and they will meet at a point here. And this is the image position. This is where image is formed. That's the trick. That's it. And if you want to F ray, so any light rays passing through the focal point will go parallel because it's opposite, right? Because any parallel light ray will go to the focus, so opposite will also is also. So basically, but just focus on P and M ray, and you do the same thing for concave lens or diverging lens. So in case of concave lens, do the same thing again. So P ray, the P ray has now diverge right through the focus, right? It just appears to diverge from the focus, and the other way you need is M ray, right? M ray has to go directly through the center and it will go undeflected. And these two ray will intersect. This is the image position in case of concave lens. Okay. And so again, the formation of the image position, whether it is virtual or real, size, all depends on the object distance. So here's change the object. This is called object distance, and this is called image distance, DI. And the focal point. This is the focal, and there's some relationship. Now, if you put it here, what will happen? So the second is, if you put an object, right? This is the object, right? Beyond the focal point, within the focal point, focus and the object distance. Now, in this case, it will form a virtual image, as you can see, right? Because this is the P ray. This is the P ray. It has to go through. So let me show you the big diagram actually. Okay. So here's what will happen. So lens. So actually, this is the P ray, right? This is the M ray. This is the F ray. But in reality, actually, it's not just three rays, right? There will be infinitely large number of light rays that will strike from each point, right? Like this. Each point will be image. So this is the tip of the right because this there will be huge number of light rays that will strike, and it forms this point, right? And this point will be imaged here, right? And this is so this point will be imaged here. This point do the same thing, image here. This one image here, and then you will see a full size of the image, right? Each point will be imaged, right? And there will be infinitely large number of light rays, but we just need P and M rays, remember. Okay. So the next is the thin lens equation. Okay, so that thin lens equation just gives the relationship between object distance, image distance, and the focal point, focal length. So object distance is the distance between the object and the center of the lens, right? Like this, from measure from here. This is called object distance. This is called image distance, and this is called focal length, F, right? And this is the lens equation basically. So it says 1 over focal point, focal length is equal to 1 over object distance plus 1 over image distance. And the magnification, right, how big the image is going to be, is given also by this formula. It has two formulas. One is in terms of object and image distance is negative. This negative is in negative di over d naught is also equal to height of the image divided by height of the object. Okay. So why you have negative sign in terms of di and d? Because it simply means the inverted image will be a real image. The real images will always be inverted compared to the object. Okay, so because you will see in calculus, that's the implication of this negative sign. Okay, here's some sign convention. Okay, so when you solve problems, lens problems, these are the sign convention you have to be careful. So focal length. If you have a converging lens, is check this as positive focal length. If the lens is concave lens or diverging lens, you must manually do the focal length before you do calculation negative. Magnification. So magnification M is positive for right upright image. If M is positive right, the image is upright. If M is negative, right, it will be inverted image. Image distance. So the image distance will be positive for real image, right? And image distance will be negative for virtual image. That's it. And object distance is positive for all. In almost all cases, actually, we'll consider, object as real object, positive distance. In very few cases, you will have to consider object as virtual, but we're not gonna do that. So, and this lens has many application actually, from optical microscope to optical telescopes. This is an example of microscope. Microscope just uses two thin lenses having different focal lengths plus separated by some distance. And first, this objective uh, will magnify the image a little bit, and then it will be further magnified by the second eyepiece lens. That's how it works. And there are some example calculations, so I can show you as a separate calculation.